master's student at Purdue University, and today I'm going to be presenting to you guys about the estimation of field variables from limited measurements using spectral theory projection methods. So a quick outline of what I'm going to talk about today. I'm going to discuss the context and motivation of the problem, describe this method I've developed, present results and analysis, and then give a summary and conclusion. So to broadly contextualize this problem, the NRC has recently tasked us, the nuclear engineers of the world, to evaluate digital twin technology for implementation in our next generation nuclear reactors. Now, what is a digital twin? Roughly speaking, it is a real-time digital representation of some mechanical or otherwise system, in this case reactor system, that takes sensed data from the environment, processes it in some way, and then presents it to human readers in a way that is useful for us as human operators and engineers to do something with that data. So these can enhance safety, longevity, and automation. Safety by providing new ways to flag transient cases more quickly. Longevity by giving future engineers long-term data about thermal fatigue stresses. Automation by allowing fewer operators to make sense of the vast streams of data coming in from all these sensors and operate the reactor based on that. All that said, one of the key challenges of these digital twins is turning data from as few sensors as possible into as comprehensive of a digital representation as possible. Sensors are expensive, and sensors are another thing to break. We don't want either of those things. We'd like to minimize it. So today, I'm going to be discussing this method that I'm calling spectral projection. I'm saying projection because we are projecting from one mathematical space to another. This can be a geometrical projection. Right here, a surface of a cylinder, say information about temperature at that surface, to information about the volume of the flow field around it, geometrical or spatial projection. We can also project between different scalar fields. So from temperature to pressure. Why we might want to do that? Temperature is typically much easier and cheaper to measure than pressure, especially in the extreme environments of a nuclear reactor. So now that I've justified this work, I'll get into the method. So I ran this experiment, or this study that I'm presenting today, on a canonical problem, von Karman vortex street, because similar methods have been around in the literature for a while and have been demonstrated on an array of geometries. I wanted today's study to be done on a relatively simple geometry and well-known problem to avoid issues of I didn't want to spend a lot of time working on grid convergence and working on making sure that my simulation for a complex geometry was very effective. I used a simple problem so that I could run simulations quickly, be confident in their accuracy that I'm then feeding into this machine learning algorithm. But I simulated a flow over a heated cylinder, as you can see here. This is a representation of the temperature and the pressure, and stored the temperature and pressure data both on the surface of that cylinder and throughout the volume of the simulation for a number of time steps. To get this data, I ran the simulation until a steady oscillatory state was achieved. Then I started logging information for both my training data set and test data set. So to develop the machine learning model, I used a mathematical technique, singular value decomposition. This is just a way to take a matrix and factor it into 3 other matrices. What this allows us to do, we take our data matrix, A1. We store the snapshots that I mentioned on the previous slide in that matrix as column vectors. So we've got time 1, time 2, time 3. The rows being different positions. So if we're talking about that cylinder domain, different points around that cylinder. If we're talking about the volume, different grid points in that volumetric space. But we factor that into 3 matrices. This middle one here is the equivalent of eigenvalues for a rectangular matrix. On the left, we have this U. U is a set of modes which form an optimal orthogonal basis from which we can reconstruct these snapshots. Now, what does that mean? All orthogonal basis means is that these modes are linearly independent from each other, and that we can add them together with different scaling values in order to attempt to recreate these column vectors here. Optimal just means that this method produces a sorted list of those modes, the first one being the most important for the reconstruction of a snapshot, second one being second most important. And so we are able to take In this study, for instance, we ended up with 209 modes. We were able to look at 5, 10, or 15 of those modes and capture most of the physical behavior. Now, in much the same way that these U modes can be added together to recreate snapshots, these V modes are in the frequency space and can be added together to recreate the time series at any individual point from this training matrix. Now, why we care about that is the crux of this method, this spectral projection. So if we have a flow, say, in this study, this flow over a cylinder, in a region where we know we're producing some perturbation from some geometry or heat source or something like that. If that's a known obstruction, it is reasonable to assume in many cases that perturbations on the surface of the cylinder, say, would also, the perturbations happening on the surface of the cylinder happen at certain frequencies. We don't have to know those frequencies necessarily, but we've stored those frequencies in this V matrix. It's often fairly reasonable to assume that in the volume, at any given data point, the fluctuations at that point in space likely also follow similar frequencies. And so we can take this factorization, substitute in a new data matrix, A2, rearrange and solve for U2. And this U2 is now no longer that perfect optimal orthogonal basis I was talking about on the last slide. But it is still an orthogonal basis, and it is a basis that assumes the frequencies that we found on the cylinder, say, are also present in the volume. And then we can run with that and perform tests on it and evaluate whether or not we made a good choice in making that assumption. But I've been talking about these U1 and U2. That U1 could be the temperature around the cylinder. U2 could be the temperature within the volume, the pressure in the volume, the pressure around the cylinder. And the success of this method will depend on the presence of those frequencies in those other domains. So before we get to making these predictions, we also have to select our sensor locations. The point of this method is to both inform us where to put sensors in our system and also maximize the information extracted from those sensors. So to do that, we examine the modes we've constructed. These are the first three modes on that cylinder domain. Our goal is to find values which scale them together to successfully reconstruct some data that we fed it in a test case. Well, to do that, if we look at this orange mode here, we can see it crosses the zero axis right here where I've got that dot set. Now, if we're trying to figure out the scaling of that mode, this location right here is going to tell us almost nothing about the scaling of that orange mode, because as we scale that orange mode, that zero value just stays zero. If we were to put a sensor over here, however, that sensor is going to capture a lot of information about the scaling of that orange mode. It's by being one of the minima or maxima, it is one of the points that is most affected by the scaling of that mode. So we place our sensors sequentially. We put 2 sensors in for the first mode, 2 for the second, 2 for the third, working our way down as the modes decreases in importance. And we can develop a list of likely useful sensor locations. We can then turn that information into this matrix right here, phi. All this does is take a column vector y containing however long our input vector is. Say that surface of the cylinder had 200 simulated points around it. That y vector is going to be 200 dimensions long. This just takes it, masks it, and turns it into however many sensors long vector we have. That could be 10 or 15 or something like that. But then we get to the reconstruction, now that we've got our model trained and our sensors selected. So we use this equation I've written right here, x equals phi u bar n. We know about x, that's our sensed data now in the test case, brand new data that we didn't train the model on. Phi is that masking matrix. U bar is simply a truncated set of modes. Rather than using all of the modes we developed, we're now just using the first 5, the first 10, the first 15. A is then that set of scaling values for the modes. That's what we're after. And so to find that, we solve this equation for A. Now I note down here, this method, the method I'm using relies on having a greater number of sensors than modes. In mathematical terms, that translates to this matrix algebra representing a system of equations where we have more equations than we have unknowns. This is important because if we were in the opposite situation where we have more unknowns than equations, then we would have an infinite set of solutions to our problem. That doesn't do us any good. We don't want an infinite set of solutions. We want one. We can use a method developed by Penrose to solve this matrix equation fairly simply and give us a least squared optimized solution where x is not going to equal phi u bar a, but it's going to be the most optimally close way that you can treat the parameters a to explain our sensed data x. Now that we've got this A matrix though, we can come back. We don't have to use the same u bar that we used to solve this equation. We can now go, instead of using u1 from over here, we can grab one of our u2s, plug it into this equation right here, and get a guess for that other domain that we didn't have any sensors in. Over here, this is just an example showing, if you really zoom in, these pictures aren't identical, but they are fairly close, kind of emphasizing the success, at least of this problem of this method. This is a matrix with a color map kind of showing some previous work that I've done on this topic, evaluating the success of this method in fluids of different Prandtl numbers. But I want to emphasize, like, you can see that our maximum absolute error across a 1,000 time step test, it hovers around 1% for a lot of cases. This method was pretty darn effective, in my estimation, at predicting these results. So in summary, before I get to the actual results of this present study, this method relies on simulating a sensed domain and an unsensed domain. So a place where we want to put some sensors and a place where we want to know about something but don't want to put sensors. We then train the model from the data, select sensors based on the trained model, and we use the model and then some fresh sensed data in the real world, or in my case, some test data that the model never saw while it was training, to predict fields in the unsensed locations in domain. So for my work, the results I'm presenting for you here today, the model was trained on temperature data from the surface of that cylinder, and then pressure data from the surrounding flow, because like I mentioned earlier, it would be really nice in some cases if we can predict pressure, say, on the reactor vessel wall over time, and log that data for fatigue analysis or similar uses. So we compare the predicted pressure data to the pressure data from the simulation and the test set. I used the maximum absolute error across 1,000 different test cases to give us a feel for, like, okay, worst case scenario, how bad is this method? And I summarize the results here across. These lines are different numbers of modes being used. The x-axis is our number of sensors, y-axis is error, lower is better. And what you'll notice is that as we increase the number of sensors, for any given number of modes, we eventually level off and reach this asymptotic error value, as I termed it. That indicates that we have used an amount of sensors that we've squeezed the rock dry. We can't get any more information out of that number of modes. Now this is useful to a designer because, as I've tabulated here, a designer could conduct this process on their system, examine the maximum error out values they get, know their design parameters, what level of error would be useful for them, say they decide 3%. They can then look, say, oh, okay, 11 modes, trace the 11 mode line back, find that point where it reaches that asymptotic error, come down here and say, oh, okay, I need 16 sensors in these locations. Great, I'm done as a designer. And so, to summarize and conclude, this spectral projection method that I've outlined contributes to digital twin development efforts by increasing the utility of limited sensors. The domain casting method can infer information in real time about an unsensed domain from sensed data using this pre-trained model relying on simulations. This method achieved error under 1% with sufficient modes and sensors, but that's not a very exciting result because of how specific that result is to this geometry. What is a more interesting and significant result, in my opinion, is that this produced a good set of data that somebody could use to tune a model for their own scenario so that they can identify the minimum number of sensors and what mathematical model to pair those sensors with to get their desired output. Thank you for your time, and if you have any questions, I'm more than happy to answer them.